I'm Alan Thorpe.
And I'm David Rogers, and together we host the WeatherPod.
In this special series on artificial intelligence, we invite leading experts to reveal how AI is being used across all sectors of the global weather enterprise.
We want to find out how business, the public sector and academia are using AI. Can it help improve the accuracy and quality of weather and climate information?
Can it help to make weather and climate information more useful and usable across a range of critical activities that are impacted by weather and climate?
There are many claims being made about AI, but what is its real value when it comes to helping business and society meet the growing climate challenge? In this episode of the WeatherPod, we invite Shruti Nath of Oxford University into the studio. Shruti's research is about using data-driven artificial intelligence or AI techniques for improving weather forecasts and rainfall forecasts in particular. The emphasis of her work is very much on linking research to action. A key part of this is collaboration with local meteorological services in the Greater Horn of Africa on the development of operational AI-based post-processing techniques. Our discussion was wide-ranging and shed much new light on the potential value of AI in weather forecasting. The areas we covered ranged from the pros and cons of using AI-based post-processing techniques for raw weather data to AI's potential role in generating much larger ensembles than are currently possible. We examined the massive step change cloud computing could bring to local forecasting capabilities by enabling weather services in developing countries to train and develop their own AI models. We also looked at the influence AI could have in coming years on the way weather information is used by weather-affected end users. Finally, we took a gaze into the future. How does Shruti think the global weather enterprise might evolve in future years in the light of the emerging AI tools she's been working with?
Shruti, welcome to the WeatherPod.
Yeah, welcome, Shruti. Great to have you on the show.
Yes, it's good to be here. Thank you for having me.
In our special series on the WeatherPod on AI for weather forecasting, we've focused on the basic tools, some of them anyway, being developed for using machine learning to make weather predictions. I guess on the other hand, your research really makes use of those AI tools, particularly for things like early warning systems, and a particular focus, I think, on forecasting events like rainfall, for example, in Africa. So I'm sure we will look forward to covering those in our discussions. And I know that the overall aim of your work is very much to translate research into action. And again, perhaps before we get into the details of that, I think listeners would be interested in your route into this subject. How have you sort of developed your thinking on this, and what's your path been to this work?
Yeah, so I originally had a background in mathematics, and I was always very interested in how we could apply different types of modeling to represent very chaotic, complex phenomena such as the weather. Um, I actually dabbled quite a bit when I used to work at the Swiss Meteorological Organization in machine learning for thunderstorm nowcasting, and that's where I really realized that it's quite exciting and also very interesting to apply certain types of techniques and machine learning models in an operational setting. Although there are some frustrations sometimes, I think it's always a very, delicate translation from the machine learning aspect to actually getting some operational usefulness to these algorithms. But yeah, I followed this sort of route of applying mathematics and modeling to weather, and also being a bit more hands-on and actually doing it in an operational setting. My PhD mainly focused also on climate model emulation, and seeing how best we could do it with the perfect compromise between computational complexity and also accuracy in the models. So it was quite natural that I eventually ended up over here.
Okay, so how did you get into sort of early warning systems and also working in Africa? How did that part arrive?
So beforehand, I used to work at an NGO, and we did a lot of work with the Intergovernmental Authority on Development Climate Prediction and Application Center. So that's a big body that has countries spanning from Djibouti down to Tanzania. And I used to work there. I'm actually originally from Kenya, so it was also quite easy for me to go back and actually work in their center. And that's actually where the first concept of early warnings was introduced to me because I always used to work a bit more on the operational nowcasting or on the other end of the extreme in the climate timescale. So this sort of concept of then linking it to actual action and anticipatory action and actually activating resources to actually deal with climate extremes was first and foremost learned when I used to visit the ICPAC office in Africa.
So one area of great importance is the post-processing of raw weather prediction data to remove systematic biases and to produce smaller scale features via downscaling and improve accuracy and reliability of forecasts. And it's various statistical techniques have existed, and we've done this for a very long time. But now AI appears to be a very powerful tool in improving the downscaling of predictions. Can you elaborate on that and how it works?
Yes, so we've sort of operationalized AI for providing downscaling of weather forecast and post-processing of weather forecasts. Currently within our project, though, a bit of background, it's the Strengthening Early Warning Systems for Anticipatory Action project. And as mentioned before, we really work with linking research to action. So we work with the local meteorological departments in operationalizing AI-based post-processing techniques. The current technique we use is a generative adversarial network. Not going too much into the technicalities of it, but it's a stochastic downscaling or post-processing method that takes in and follows a hybrid approach. So it takes in the integrated forecast system, weather forecasts, and is able to correct any structural errors that are present within them to provide more accurate rainfall forecasts. The main step change that we have observed over here when actually operationalizing this in the local meteorological department is that it provides a very cheap, let's say, easy way of doing the post-processing and downscaling as compared to the limited area models that have been used before. And this follows a line of reasoning coming from my professor Tim Palmer's white paper, where he really discusses the future of AI within the weather context and weather modeling context, especially for operational purposes and use cases. And typically, limited area models are quite computationally heavy to run, and also it's difficult to make the reforecast necessary to validate them adequately and derive test products. AI from our project as well has come in here and really sort of taken away the need for computational infrastructure since now the local meteorological departments can run this post-processing system in a very computationally affordable way on their infrastructure, which is a massive step change.
So you're starting with, but you're still starting with the sort of the an integrated forecasting system such as a DCMWF and so forth. So unlike other approaches, which are sort of saying, well, we'll take everything, everything will be statistical, you're still using the numerical processes, the numerical weather prediction as a basis for this kind of work. Is that correct?
That's correct. At least over the tropics, what we've seen is that rainfall is quite difficult to forecast. So even the integrated forecast system isn't very good. And unfortunately, it's also an area that's quite data sparse. So we don't really have so many observational networks. But AI still provides a data-driven approach to provide better, more accurate rainfall forecasts. We follow the hybrid approach mainly also because it provides us a foundational basis on which we know that there is some physics involved still from the integrated forecast system, but we're really just looking at correcting the structural errors that are present within them. Um, and from an operational perspective, I think this also gets us a lot more buy-in because the forecasters at least know where the forecast is coming from. So they know that it's post-processed based off this IFS forecast, which gains also a bit more trust in the model because there is still some physics in it, especially for a place there the precipitation is notoriously difficult to predict and requires a lot more physical understanding.
Can I just follow up a brief point? I don't. You've described very well some of the difficulties actually of tropical rainfall prediction and the fact that there are limited data and even the physical processes are perhaps less well understood. What I can't understand though yet from what you've said is how can machine learning help? I mean, if we don't have that data that you talked about for precipitation, how does the machine learning learn, so to speak, to add this value?
It's a really good question. I was also initially very skeptical when I started off. So, a bit of background context. The integrated forecast system, IFS, currently doesn't perform as well as climatology for rainfall forecasting over our region. Um, and before trying out the machine learning, let's say more generative adversarial network approach, I'd also tried out some other approaches such as simple autoregressive processes that have a bit more spatially correlated terms. And it was really fascinating to realize that the generative adversarial network, the GAN approach, this AI-based approach, when trained correctly, could really ingest a lot more spatial information to provide more accurate results as compared to any other statistical method of downscaling. And I'm not entirely sure where that's coming from, but my guess is it's taking in a lot of information from, for example, Cape or also wind, and all these variables that we really feed into it. And it's sort of learning where and under what scenarios the IFS has certain structural errors and biases, which it then corrects. So it's not necessarily contingent on the observational data that we have lacking, but more so on how much forecast data we have so that it can really learn these inherent structural biases much more correctly. And also it can learn it in a way that's also very spatially distributed. So it really ingests all that spatial information and can really work in this sort of higher dimensional space, which I find quite fascinating.
So in a way, you're saying that this method can learn from the errors that exist in, if you like, the traditional physics forecasts. And I guess that's always been the case for post-processing, isn't it? You look back at how poor or how good your forecasts were in the past. But even, all of these approaches require some way of knowing what the truth is, what actually happened. And as we've said, some of the precipitation, particularly data, and particularly in areas like Africa, are those evaluation information of what the truth is also somewhat limited. I don't know. Would you agree with that? I mean, is that a bit of a problem?
It is definitely a bit of a problem. Right now, we rely on satellite data. So we use the iMerge satellite product as our truth. Working with the local meteorological departments also gives us a significant advantage in a sense because they also have their rain gauge data that, although we wouldn't guess directly, can be assimilated into certain satellite products. And this allows us also to evaluate, let's say, a bit closer to the truth or the ground truth, especially when it comes to capturing extremes. But it is a difficulty and it's a problem that's, you know, something that's difficult to really get across, or really difficult to get over. But currently, we use the satellite products that seem to at least provide as much information as would be needed for early warning systems or to our end users.
So just to follow up a little on that. So if you had a choice of what you could afford to focus on from a country perspective, you're sort of, if I understand correctly, you're saying that basically if you enhanced your observational network for your rain gauge network, for example, and then you put your effort into replacing or not using limited area models per se, but actually using an AI algorithms for the downscaling aspect, and then allowing that to utilize the observational data that you have from within the country, you'd end up with a much better forecast. Would that be true?
Precisely, that would be true. And that's really what we're working towards. So it's always, you always have to go one step at a time. So first build confidence in the fact that this AI post-processing system as an alternative to the limited area model is viable, that it has some operational benefit. Because currently there's a lot of models out there, and I feel like they keep making a new one every week. But it's always, a certain, let's say, marginal improvement in accuracy, or it's always some sort of improvement that when you translate it to operational purposes isn't necessarily clear. It's very abstract. And right now we're really focusing on building that confidence that, okay, apart from this improvement in accuracy, what else can you do with the AI? Well, you can run it instead of your limited area models. In that sense, you can also have a bit more of a computationally cheap way of generating forecasts that's also maybe a bit more interactive. And in that way, we get a bit more confidence in how viable it is operationally speaking. And then the next step would be, well, we've got it currently trained on this observational data. Would you like to improve it? And eventually, well, my vision would be that they would be able to train it themselves and be able to train it on their observational data themselves, which would then also give them a bit more idea of where they have a bit more data gaps, so to say, where they would need a bit more observational network strengthening. And then they would be able to always constantly assimilate that into their own model.
I think this has been a very interesting part of our discussion, for me anyway, because I think you've hinted that really this is a very hybrid approach. I mean, in essence, you need the physics description of the processes, particularly on the larger scale, to complement both the observations, limited though they are, but also with the ability to statistically analyze and remove the sort of errors that we find in traditional models. And that's a better route than actually having a much higher resolution physics-based limited area model. So I mean, it's which has been the approach up to now. I mean, is that a fair summary, or am I glossing over too much to say that?
I think that's a fair summary. I mean, there is like a bit more nuance to it, obviously. I think this approach works quite well in the short range forecasting. So, going up to 10 days after, which we see that we hit a bit of a wall and we're not necessarily doing as well as climatology. Um, and coming to that, I do still think there is value on having high resolution numerical weather prediction developments, although if it's within the capacity of limited area model, I'm not so sure. Maybe a bit more of a global effort is what we need, because for medium range weather forecasts, at least, the skill can be relatively poor if the upstream initial conditions aren't so well understood most of the time. And I think there is still value to efforts, especially when we want to go towards that medium range of having higher resolution models. But within the timescales that we work on, so the short range, the AI-based alternative following this hybrid approach that's able to run every sort of scenario of what error and structural bias could exist in the numerical weather prediction model and then produce more accurate regional predictions is much better. Also, there is a computational aspect to it where I think typically a lot of the AI models that are used for weather forecasting forecast a large range of variables. So they forecast, not just rainfall, but they forecast wind, shortwave radiation, CAPE, and all these other variables, whatnot. And that amounts to a vast amount of data in the end. And to run that locally within the meteorological departments that we work with would still be quite heavy. The hybrid approach allows avenue for a much more sophisticated, slim model where we really just focus on rainfall and we just focus on a certain region. And that means that it's much easier to train and also much easier to run, and also gets a bit more buy-in because the forecasters know that it's based off this physical model, especially again within their area where rainfall is notoriously difficult.
Another interesting aspect that just pops into my mind is a lot of limited area models that are used don't have data assimilation at all. So you're actually using AI, training your AI at the local level with data. So you have rainfall data that you would not actually utilize in a limited area model, relying entirely on the large-scale model to provide the boundary conditions and de facto the assimilation. And it's quite interesting. It seems that countries would be able to make much better use of their own data in this process, and I see that as quite valuable. That's really interesting. Can we talk about ensemble prediction? When we talked to Tim some time ago, and he was talking about using AI to create a 1,000-member ensemble, I think he said. Can we talk a little bit about just how that would work, and how AI actually achieves that in that rather complex situation? It's complex modeling process.
Yeah, so we use generative AI-based techniques, and this is sort of akin to, I guess you guys know DALI and these other image generator AI models that you can just put in some sort of prompt and then it would generate an image. And in this case, the prompt is really just the weather forecast from the forecast system. And it will be able to just generate all the possible scenarios that are related to that prompt. And in that sense, you can explore the initial condition uncertainty space based on this initial prompt that you put in, following the generative AI techniques. Our particular model is a generative adversarial network. And just to give a bit of a, let's say, very rudimentary explanation of what it does, is it consists of a generator and an adversary. And the generator's job is to take in these initial conditions or the initial forecasts and generate very realistic images of what they would actually look like in terms of the observations. And the adversary is only there during the training period, and it knows what the actual observation looks like. And so based on what it knows, it will assign a score to what the generator produces of whether it's realistic or not. And in that sense, you can get a model that's able to generate very realistic looking images that also explore the uncertainty space, and in the end is able to explore also the initial condition uncertainty space and generate lots of different ensemble members or images, so to speak. Once trained, it's extremely cheap to run. So to put it into context, generating around 50 ensemble members is 3 minutes on a laptop, which you can imagine is a massive gain compared to what it traditionally takes to generate ensemble members. And so you can push that up to 1,000. And that's just adding on 2 minutes or so, depending on what sort of laptop or desktop you have. And so, in effect, you can get a 7 minute, 1,000 ensemble member forecast from this generative AI-based approach.
I mean,
when you sorry, Alan, go on.
One of the things that I've heard about this, thousands of members of an ensemble, is that yes, you can add lots of members to the ensemble, but in the end, all you're doing is looking at, in a sense, the uncertainty about the mean, about the ensemble mean, if you like, so that if there's a sort of a probability distribution that's like a Gaussian distribution, as you add more and more members, you just make it much more like the Gaussian function, rather than anything else. And it's not really, in that sense, looking at a simulation of independent states, of realizations, of situations where there might be a storm that comes over your area, another simulation that doesn't have a storm at all, or the storm goes somewhere else. And that gives you actually a whole set of simulated atmospheres, futures, if you like. So to me, the argument I've heard is that maybe, yes, you can use AI to generate thousands of members, but they're not necessarily giving you that kind of range of independent realizations. Is that correct, or how do you see that?
It depends on how your AI model is trained because there's a lot to do with imbalanced learning. So some people, they really train their models on only extremes, for example, or some people, they only train their models on the usual conditions. And the idea is that the AI model would be able to actually learn the physics so that it would be able to predict out of sample extremes. And there have been a lot of situations in where people have seen that the AI model, once trained, can perhaps predict these out of range or out of sample extremes, so these other sort of atmospheric conditions. Um, so in a sense, actually, the distribution that you get is not necessarily always Gaussian or around the state mean. It can sometimes actually predict these different scenarios, or that's what we've seen as well. Particularly for rainfall, we all know that that's a very difficult distribution to work with. It's quite exponential or power law distributed, so to speak. And so being able to capture those real outliers with a larger ensemble is actually what we're aiming for right now and what we're hoping for. Although there is always some issues. So a lot of AI models tend to smooth, and so you don't always get that extreme, but you can get an indication of whether there is more uncertainty, whether there is more likelihood of a certain extreme. More so with a larger ensemble, you can get a better idea of what the true underlying distribution is looking like. And especially for an operational purpose, I think that's quite valuable because if you've only got 50 ensemble members for such a strange exponential distribution, well, then your mean is really also going to be much different compared to whether I make it and whether you make it, for example. So if I generate 50 ensemble members with my AI model and you, Alan, generate 50 ensemble members and we calculate the mean, it might be very different just because distribution of rainfall itself is so tricky. But if I generated 1,000 and you generated 1,000, our mean might converge a bit more and we would have a better understanding of what's going on. And then particularly for extremes, that sort of translates because you can get a better understanding of what the likelihoods are of certain extreme events. And essentially, or eventually, I hope for operational purposes, the use of larger ensembles might help us match or map from the true underlying distribution to what the expected probabilities are for specific thresholds that our end users are actually interested in. And of course, a larger ensemble allows you to have a better understanding of what your true underlying distribution is in the end.
Okay, I mean, if I could just move on our discussion. David and I work quite a bit with the World Bank, particularly on how the if you like, the digital transformation that we're all observing is taking place and benefiting, hopefully, developing countries. And obviously you work in some developing countries as well. And that digital transformation hopefully will make weather information, enable better saving of lives and infrastructure and also economic benefit. Previously on the WeatherPod, we've discussed that part of that digital transformation is about cloud computing and about the ability to use. I mean, I'm just thinking of the European Weather Cloud as an example of a new initiative to enable data access and computing to be done via the cloud. I just wonder if you could say a little bit about how you see that playing out in the areas of work that you're involved with in developing countries.
Yeah, so the cloud is a massive step change in the developing country weather forecast area, mainly because they typically don't have access to GPUs. That is something that I've realized I take quite a bit for granted over here. But that means that it's very difficult to train an AI model because a GPU is a massive speed up in terms of actually training your model and being able to train it longer and actually achieve a certain performance gain. The cloud enables access to GPUs. So instead of having to train it locally on a CPU that would probably take weeks. They can already just have access to the cloud GPU. What that also means is that they get to have more interaction with the AI model development, which is key also. Again, we want these people to be able to develop the models themselves in the end and also assimilate directly their data to it, or that would be what we would hope for in the future. Another really interesting development in that aspect is also that there's a huge push for what's called analysis ready cloud optimized data that follows what's called FAIR principles, so findable, accessible, interoperable, and reproducible. And there's a big community that's growing right now to actually have a lot of this analysis ready data available on the cloud, following formats that are also very easy to access once you're also working on a virtual machine on the cloud. What that means is also that instead of having to download a lot of data that then you would use and have to post-process for training your AI model locally, you can just access it from the cloud and pull it into your virtual machine. And in essence, you can stream it through your model while training. And that is a gain in terms of time of days, because typically, it takes me at least 1 to 2 days to set up my data pipeline. And that is actually a big part of the AI model development. It's the data pipelining. And with the cloud, you can just stream it through and train your model with access to GPU on the cloud and eventually develop your model, fine tune it, and continuously assimilate data into it as well. And in that way, it also allows much more accessibility to regions that typically don't have GPUs.
So the GPU is I hadn't fully realized this, but you want the weather cloud system of the future, because I don't think we have it necessarily at the moment, to be a set of computational facilities in the cloud that are GPU based. Is that your picture of how it might work?
Yes, that would be sort of an ideal world for me, because that would mean that anywhere or anyone anywhere in the world could train their own AI model, and more so access data on the cloud to do so, which would then lead to much more, you know, independence in terms of AI model development. You wouldn't really have to always have investment into GPU infrastructure on the ground. But
But the,
obviously, that also comes with its cons. You would have to rely on the cloud. You wouldn't have much more resilience on the ground in case, for example, you lose internet or don't really have any connectivity.
so does this mean that really there's a big push forward to have international cooperation to generate these accessible cloud GPU systems? I mean, thinking about a particular developing country or countries, they will have to presumably ultimately pay to use these cloud, but someone has to provide the cloud computing. And is that do you see that as a kind of, I mentioned the European weather cloud before, that is to a degree a collaboration amongst some European countries. I don't know how GPU based it is, but at least it is a cooperation. Is that what we're looking at? Are we going to see or need to see better international cooperation to generate this?
I would think so. I think
Okay.
that would really go towards a much more sustainable uh, development in terms of how AI models are integrated into local operational facilities. Because in reality, if these national meteorological services cannot develop their models themselves or do not have access to GPUs, and even if they do get access to GPUs, let's say there's issues with power, with maintaining the GPUs, with resources for that, the cloud provides a very easy, let's say, more community maintained alternative to that. So in an ideal world, that would be one avenue for pushing towards it. And not just, access to graphical processing units or GPUs, but also access to data on the cloud. That would also facilitate much quicker development of models, because you wouldn't have to download it. You'd just be operating up there on the cloud.
It's a very interesting area from the point of view. One is getting countries to recognize that cloud computing, not having a physical piece of hardware in your office, is a reasonably good approach and is secure, and is actually probably more secure than having a piece of hardware in your office. And I was wondering, in your experience and where you've been working, whether you find the people you work with are receptive to that approach. Because we often, as Alan has said, we're working with a lot of different countries, and their immediate response is no. We have to own it because of security, and then you realize that actually that's bogus because they have more trouble with maintaining the security of their systems. But what's your sort of experience with the people you've been working with?
They're actually within the ICPAC, which is the main point of contact for our cloud developments. They're extremely receptive, and I think they really acknowledge that this might be a better avenue in terms of entering the age of AI, so to speak, and entering this age of large data and data-driven techniques. Having access to a cloud infrastructure that's community maintained and that can be secure is actually going to be very helpful, very meaningful for their operational activities. Um, there's also movements such as that of federated learning, which is actually not so new. It's been there for quite a while, where you have a secure sort of data server, and the person developing the model doesn't get to see the data, but they get to train their model on it and provide the weights and the parameters of their models. So there's avenues and approaches to actually go about, let's say, data security or privacy issues. What I have also noticed working on the cloud and also developing these pipelines on the cloud is that there is a massive open source community surrounding it. So we interact with a lot of other people from different sectors that also work on a similar thing, or from academia research that work on making these sorts of cloud optimized data sets and also making them usable for everyone because that's just in everyone's interest that we can exchange this because we are in the age of data. And so really what I've seen is that the open source community has been very beneficial as well because it means that everyone from everywhere can interact and really exchange and share knowledge on what their experiences have been with working on the cloud. And that has also helped us a lot in terms of actually, let's say, going around issues, not reinventing the wheel, and also having a much more concrete, coherent objective in terms of what the cloud development for operational purposes within the ICPAC, for example, would be.
You touched on, you mentioned anticipatory action early on, and one, of course, really important, the purpose of a weather forecast is not the beauty of the forecast, but how it's used and how people are able to interact with that information and utilize it in a really effective way. And I'm curious from the work that you're doing, how you see the sort of the ultimately the end user's interaction with these forecasts, with these basically AI tools, not just the tools that are helping you generate the forecast, but also tools which are helping them interpret the information effectively for their own application. Does your work sort of lead to that?
It does. We really work closely with the local meteorological departments in operationalizing the AI tools. And one thing that I always love seeing is them generating the forecast on their laptops because it's that interactive, right? They can just do it, which was previously unheard of. And one person will generate it, and the other person will generate their own set of forecasts, and then they'll compare what they've done. And it's really fun because you can really see that it's made weather forecasting much more interactive. And then they'll do it for, let's say, 1,000 ensemble members or 50, and they'll look at what the difference is and whether they see this one like severe event on one laptop compared to the other, or it just allows them to really compare and interact with this whole process of weather generation, which before was very much a black box, which is also quite funny because we will think AI is a black box. But in reality, of course, we don't really know everything that's going on inside it. But it's allowed people to have a much more interactive way of generating weather forecasts. which has also led them to really be curious about it and really want to use it operationally and really do it every day. And I think that's really interesting because it's, in a sense, gotten a lot more buy-in in terms of this might be what we want to do in the future. Um, and then speaking about translating it into something that's also important for their operational activities, obviously, in the end, um, we've all pivoted or are still pivoting towards ensemble forecasts. And I think the AI pivot goes hand in hand with that because now they have this much more interactive way of exploring the ensemble space and the forecast space. And eventually, the idea is, though, that they should still be able to translate this to a yes or no, especially in the context of anticipatory action, into a yes or no. There's going to be a disaster. We need to mobilize resources and we need to act. Um, and the use of AI for that is still, let's say, still up in the air in terms of where the actual benefit will be. But what we are seeing is that with the larger ensemble forecast, again, we have this better mapping from what the true underlying probability distribution looks like. And we can then map that into what the true expected probability of given thresholds are. And these can be user defined, so 50 millimeters or so. But knowing what the true underlying distribution looks like, because we can in fact explore the space a bit more agilely and quicker with the computationally affordable AI, we can have a better mapping to what the true expected probability of certain disasters is. And in this way, this can allow you to trigger or not trigger based on what your cost of action versus inaction is. That always is up to the decision makers in the end. But at least there is this better mapping from what your true underlying distribution is to what your true expected probability of an event is, given
But
that we
that
can generate large odds.
shouldn't that also give you the opportunity to from a decision maker's point of view, because you can utilize that information to look at that distribution in a way that's more informative than we currently. So rather than it being yes or no, you understand the what ifs more specifically from that forecast distribution. That you can actually identify the potential impacts and make decisions more reliably on the impacts that you can actually predict. So you can move from the forecast to the forecasting of the actual impact using the technique, and that could be much more powerful from a decision-making point of view.
Precisely. There's a massive push towards more impact-based forecasting overall, also in the humanitarian space, and AI does provide a very good avenue for that. Because, as you said, you can explore the what ifs a bit more and you can then link it to a certain impact and then assess the cost loss of actually making a decision of that impact. And it's a bit more of like a robust way because you also do have a better idea of what the probabilities are looking like, what your expected probability is. And there is much more update and ability to have reforecast to validate that and see where you've gone wrong. Let's say if you did have a misforecast and lost, let's say, a significant amount of your resources because of acting in vain. It does allow much more scenario exploration in that sense, especially for impacts.
Great. I think sort of finally we wanted to just gaze into the WeatherPod crystal ball to see how you think the future looks. Maybe 10 years ahead in terms of these new tools that you've been working with, and I suppose in particular, what's the degree of optimism that you have about whether, in a sense, sustainable improvements can be made for operational functions in developing countries where at the moment their resources are pretty limited. So look forward for us and tell us how you think this will all pan out in a decade's time.
Oof, that's quite difficult, but looking forward, and I'll be very optimistic and hopeful over here. I do think access to better cloud computing infrastructure is going to be a massive gain because places with less infrastructure will be able to access data on the cloud. will be able to seamlessly enter this age of data and also be able to train their own models and do their own data assimilation, which would be a dream. Um, so that would be the main optimism. And I think that's sort of the next step here, because once we've entered this age of, let's say, much more democracy in terms of usage of GPUs through the cloud infrastructure, it still needs to be translated into operational usefulness or meaningfulness. And so being able to go forward, being able to develop these models, we still need to also understand the impacts attached to them and work very closely with on the ground users in developing thresholds to then use and translate these very nice, accurate AI forecasts into actual action and early warning systems.
What That's interesting. What do you think about? I've detected over the years a desire from users of weather forecasts and right through to decision makers of not just wanting to know what's going to happen in terms of an accurate forecast, but why is it happening? Why is this storm going to yield an extreme event, and why are these implications that are coming out of the predictions? It's about, to some extent, the trust that the users can have in what we're predicting. And again, one critical point one can make about AI is, and you've mentioned it already, to some extent there's a black box element to it. We don't know exactly how. Is that going to be a bit of a blocker on this development, or not?
I think it might be a blocker, and I'll pick from a very tangible example here, which is Lake Victoria, where it's known to be very difficult to predict about. It's a notorious climate of its own with a lot of thunderstorms, and really a lot of fishermen are victims over there, and would benefit from very accurate forecasts. And I think AI could come in there and potentially revolutionize it and give very accurate forecasts. But I do still think there is a lot of value into understanding why um, Lake Victoria's climate is the way it is. And I think there's still a lot of efforts into actually exploring that. So I don't think, it's one or the other. I do think there is still a lot of value into developing better climate models or weather models, and more so higher resolution ones. Because going back to something that we already touched about is when we go up to medium range forecast, AI models also seem to be predicting quite well on a seasonal scale, but that might also be, playing a bit of devil's advocate over here. That might also be because the numerical weather prediction models themselves have their skills so degraded by then. So it's still very important to try and understand the physics of what's happening and what we're missing out in terms of data assimilation, specifically for, given use cases, as I mentioned, Lake Victoria, and also for having better predictability for longer range forecasts. So the what if is still very important, and the future developments don't have to be one or the other. I think AI is, in a sense, giving much more access to weather generation and interactive generation within the National Meteorological Services, but we still need to understand what's going on, especially with climate change and changing boundary conditions where we might see more extremes and severe weather events. We still need to know exactly what's driving them.
That's really fascinating, and I like the future, I think. So, so many thanks, Shruti, for joining us on the WeatherPod today. And I really think we've actually learned a lot about the importance of AI, but also not losing sight of physics, which is pleasing to Alan's ears, absolutely, I'm sure.
Hopefully not just my ears, but yeah.
Right now, I think for all of us. So I think thanks a lot. That's been really interesting discussion with you.
Yes, many thanks, Shruti, and I know that your work in this area is perhaps at the beginning of a extensive set of developments in these countries, and I'm sure David and I, particularly with our hats on with working with the World Bank, would be really keen to see how your work develops, and it's going to be very important actually for the developing countries. So we want to encourage you and support you in what you're doing. So, but it's been a great conversation. Thank you so much.
Yeah, thank you. It's been really nice. I have to say, I also learnt quite a bit. So it's been nice to know that. I think it's always nice to hear a bit more of the nuanced approach into things.
Well, that concludes this episode of the WeatherPod. We hope you've enjoyed it. Alan and I will be back next month, and in the meantime, please give us your feedback via email to support@gweforum.org.